The universe is a vast and ever-changing stage, a cosmic theater where stars play the leading roles in an epic drama that spans billions of years. These celestial actors are born in the dense clouds of gas and dust, known as nebulae, where gravity pulls the material together to form new stars. They shine brightly for millions or even billions of years, providing light and warmth to the planets that may orbit them. But like all actors, stars have a final act. When a star exhausts its nuclear fuel, it undergoes a dramatic transformation. Depending on its mass, it may swell into a red giant or explode in a supernova. The remnants left behind, such as white dwarfs and neutron stars, are the focus of our exploration today. These remnants are not just the end of a star's life, but the beginning of a new chapter in the cosmic story. We will delve into their formation, their unique properties, and the incredible forces that govern their existence. White dwarfs, for instance, are the remnants of medium-sized stars like our Sun. Our journey begins with a look at stellar evolution, the life cycle of stars. From their fiery births in stellar nurseries to their spectacular deaths, each stage is a testament to the power and beauty of the universe. From there, we will explore the strange world of white dwarfs, where matter is squeezed to unimaginable densities, creating objects that are incredibly dense and hot. We will then venture into the realm of neutron stars, born from the fiery death throes of massive stars. These stars are so dense that a single teaspoon of their material would weigh billions of tons on Earth. Our exploration will also touch upon supernovae, the cataclysmic explosions that mark the end for some stars, releasing more energy in a few seconds than our Sun will in its entire lifetime. And black holes, the ultimate cosmic abysses where gravity reigns supreme, pulling in everything, even light, into their inescapable grasp. Join me as we unravel the mysteries of these cosmic remnants and gain a deeper understanding of the universe's grand cosmic drama. Together, we will explore the final acts of stars and the incredible phenomena they leave behind, enriching our knowledge of the cosmos. Stars, like living beings, go through a life cycle. They are born, they live, and they die, each stage marked by fascinating transformations. They are born from collapsing clouds of gas and dust known as nebulae. These regions are often referred to as stellar nurseries, where new stars are constantly being formed. Once formed, stars shine brightly for millions or even billions of years, depending on their mass. During this time, they undergo various changes in brightness and size. The lifespan and ultimate fate of a star are determined by its mass. Massive stars live fast and die young, while smaller stars like our Sun have much longer lifespans. Stars like our Sun, relatively small and average in size, spend most of their lives fusing hydrogen into helium in their cores, releasing tremendous energy in the process. This process is what makes stars shine so brightly. This is the main sequence stage where stars spend the majority of their lives. During this stage, the balance between gravity pulling inward and pressure from nuclear fusion pushing outward keeps the star stable. As they age, these stars run low on hydrogen fuel in their cores. When this happens, the core contracts and heats up, leading to the next dramatic phase in a star's life. The core contracts and heats up, causing the outer layers of the star to expand dramatically, transforming it into a red giant. This phase is marked by a significant increase in the star's size and a change in color. Eventually, the outer layers are expelled into space, forming a beautiful planetary nebula, a glowing shell of ionized gas that can be seen across vast distances in space, while the core collapses under its own gravity, forming a white dwarf. This dense, hot remnant will slowly cool and fade over billions of years, marking the final stage in the life cycle of a star like our Sun. White dwarfs are the remnants of low-mass stars like our Sun. They are incredibly dense, packing the mass of the Sun into a sphere roughly the size of Earth. Imagine squeezing all the matter in our planet into a sphere the size of a city. That's how dense a white dwarf is. The formation of a white dwarf is a dramatic process. As a star like our Sun exhausts its nuclear fuel, it can no longer support its own weight. The core collapses, and the outer layers of the star are expelled into space, creating a planetary nebula. The remaining core, no longer generating energy through nuclear fusion, continues to collapse until it reaches an incredibly dense state. At this point, a new force comes into play: electron degeneracy pressure. Electron degeneracy pressure is a quantum mechanical phenomenon that arises from the Pauli exclusion principle. This principle is a fundamental concept in quantum mechanics, dictating the behavior of electrons in atoms and stars alike. The Pauli exclusion principle states that no two electrons can occupy the same quantum state simultaneously. This rule is crucial in understanding the structure of atoms and the behavior of matter under extreme conditions. In a white dwarf, the electrons are squeezed so tightly together that they are forced into higher energy levels. This compression happens because the star has exhausted its nuclear fuel and can no longer support itself through fusion reactions. This creates an outward pressure that counteracts the inward pull of gravity, preventing the white dwarf from collapsing further. The balance between these forces is what keeps the white dwarf stable, despite its incredibly dense nature. It's a delicate balance, the immense gravity of the star's mass pushing inward, held in check by the quantum mechanical pressure of the electrons pushing outward. This equilibrium is a fascinating example of the interplay between quantum mechanics and astrophysics. One of the most famous examples of a white dwarf is Sirius B, the companion star to Sirius, the brightest star in our night sky. Discovered in the 19th century, Sirius B has been a subject of extensive study due to its unique properties. Sirius B is slightly more massive than our Sun but is incredibly small, with a diameter only slightly larger than Earth's. This makes it one of the densest objects known, with a mass packed into a volume comparable to our planet. Section 5. Neutron Stars. From supernovae to extreme density. While white dwarfs are formed from the remnants of low-mass stars, neutron stars are born from the death throes of much more massive stars, typically those with masses 8 to 20 times that of our Sun. These stars live fast and die young, ending their lives in spectacular explosions called supernovae. During a supernova, the core of the star collapses catastrophically, reaching even greater densities than those found in white dwarfs. At these extreme densities, the electrons and protons in the core are forced to combine, forming neutrons. This creates a neutron star, a sphere of almost pure nuclear matter, incredibly dense and incredibly hot. Neutron stars are even smaller than white dwarfs, typically with diameters of only about 20 kilometers. That's about the size of a city. Section 6. Pulsars, cosmic lighthouses. Many neutron stars are also pulsars, rapidly rotating objects that emit beams of radiation from their magnetic poles. These beams sweep across the universe like the beams of a lighthouse, and if Earth happens to be in the path of the beam, we detect a pulse of radiation. Pulsars are incredibly precise timekeepers. Their rotation rates are so stable that they can be used as cosmic clocks, allowing astronomers to study a wide range of phenomena, from the properties of interstellar space to the nature of gravity itself. The discovery of pulsars in the 1960s was a major breakthrough in astronomy, providing the first direct evidence for the existence of neutron stars. Section 7. Supernovae, stellar explosions that rock the cosmos. Supernovae are among the most energetic events in the universe. They are the explosive deaths of massive stars, briefly outshining entire galaxies and releasing as much energy in a few weeks as our Sun will emit over its entire 10 billion-year lifespan. There are two main types of supernovae. Type Ia supernovae occur in binary star systems, where a white dwarf is pulling matter from its companion star. When the white dwarf accretes enough mass, it can no longer support its own weight and explodes. Type 2 supernovae occur at the end of the lives of massive stars. When these stars exhaust their nuclear fuel, their cores collapse, triggering a shock wave that rips the star apart in a supernova explosion. Section 8. Black holes, where gravity reigns supreme. If the core of a collapsing star is massive enough, even the incredible density of a neutron star cannot prevent further collapse. In these cases, the core collapses indefinitely, forming a black hole. A region of space-time where gravity is so strong that nothing, not even light, can escape. Black holes are among the most mysterious objects in the universe. They are defined by their event horizon, the point of no return, beyond which nothing can escape the black hole's gravitational pull. While we cannot see black holes directly, we can detect their presence by their effects on surrounding matter. As matter falls into a black hole, it heats up and emits radiation, creating some of the brightest objects in the universe. Section 9. Conclusion. Cosmic ashes, stellar remnants. White dwarfs and neutron stars are the remnants of dead stars, but they are far from being insignificant. They are cosmic laboratories where we can study the fundamental laws of physics under extreme conditions. These remnants also play a crucial role in the evolution of the universe. Supernovae, the explosive deaths of massive stars, enrich the interstellar medium with heavy elements, seeding the universe with the building blocks of planets and life. So, the next time you gaze up at the night sky, remember that even in death, stars leave behind a legacy that continues to shape the universe we live in.